Welcome everybody. So today the second lecture. It will be totally independent of the first lecture. No knowledge of first lecture will be needed for the second lecture. I have two little remarks concerning the first lecture. Both resulted from my communication with Joseph Osterle. First, Joseph noted that there was some little mistake. So I made before Dobrovolsky's argument, I made two lemmas. One of these lemmas is not completely true, so one should be a bit careful with it. So I will, but in any case, I will return to these lemmas on the very last lecture, and I will rectify it. I will correct it. So do not worry. And the second thing, also, Joseph sent me a very simple proof of the Euler-Schoenemann congruences, just in any level. Or it like Deline's, it uses Witt vectors, but it is simpler than Deline's. So I uploaded it to the same folder where the other documents are, so you are welcome to consult it, and thanks to Joseph. Okay, so today we will speak about transfinite diameter. Our main reference will be a book of Goluzin. It's an old Russian book from 50s, so it's almost 70 years old. It was translated into English. The quality of translation is mediocre, but well, it is readable. We will just need one little section. I copied it and uploaded to the folder. I will more or less follow this section, but well, certain things I will treat slightly differently, not from point of view of ideas, but just from point of view kind of notational or whatever. Transfinite diameter is very classical notion. It was introduced almost 100 years ago in the work of Fekete. And in fact, it was known, but well, perhaps under different names, I believe, before Fekete. Fekete, an article of 1923. Quite well written, but well, it is in German, so not everybody likes to read in German. But if you can read, it's a pleasure to read this article. Very good article. But also exposition in Goluzin's book is also very good. So there are several definitions, even in this little Goluzin's section. He gives two definitions and shows the equivalence of two definitions of transfinite diameter. And I will use for the purposes of this course, it will be convenient to use a definition in terms of Chebyshev's polynomials of a compact set. So I will now quickly introduce this definition and show some properties of transfinite diameter. Calculate transfinite diameter of some important sets, and then we will see how we continue. Okay, so everywhere here will be K, will be compact set. On complex plane. And well, I said on the previous lecture that P is a prime number. There will be no prime numbers in this lecture, so we are free to use letter P as a for polynomial. So P of z, let P of z be a polynomial. And I will use notation, the norm of P with respect to K is just what we expect, is just the sup norm, the maximum of, maximum of P of z, where z runs through the set K. So the biggest and absolute value of this polynomial on K. And we are going to consider it polynomials. It will make sense to consider monic polynomials. Because, if we want to estimate absolute value, if we multiply polynomial by some scalar, we can get as small as we wish. So we should impose some normalization. So normalization will be that we will normally consider monic polynomials. And now we want, among these monic polynomials of given degree n, we want to find the one which is has smallest norm. So we denote by first mu n. We denote by mu n. Well, at this moment I just put infimum. Where P is a monic polynomial of degree n. And the first observation that actually in this infimum is minimum. So there exists indeed some polynomial where this mu n is attained. Well, why? This is obvious if the set K is finite. Now assume that K is infinite. And consider some big number, bigger than mu n. Denoted A. And we study the set of polynomials P, not necessarily monic, of degree bounded by n and of norm bounded by A. And I claim that this set is compact. Because why? If we have an infinite set, then so this set is compact. Because when we have an infinite set, when K is an infinite set, so we can just pick n plus 1 points, and we see that the values of our polynomials are bounded at n plus 1 points. And this implies, by Lagrange interpolation or whatever, that also coefficients are bounded. because the values of P at some n+1 points, we just pick some n+1 points, whatever, of K are bounded. And it follows that the coefficients are also bounded. Coefficients are bounded. So coefficients bounded, degree bounded, so we have a compact set. So we have a compact set. And monic polynomials in this set, monic of degree n, they are closed subset here. Monic polynomials also with norm bounded by A are also form a compact set. And so this implies, and this function is of course continuous, so means that it attains its smallest value. So continuous function and compact set, so there exists some polynomial that denote Tn, monic of degree n, such that its norm is exactly our mu n. Yeah. And it is often called Chebyshev's polynomial of degree n for
Please, Yuri, is it always unique?
Oh, this is a very good question. I believe yes, but I don't know how to prove it. But I don't think that we ever need uniqueness. Goluzin kind of avoids discussing this topic. I don't know. I believe that somewhere in Chebyshev was actually who introduced these kind of polynomials. And believe he somewhere proves that it must be unique, but well, I don't know. To be honest, I don't know. I believe yes, but I don't know how to prove it. But anyway, I don't think we will ever need it. Yeah, and so nth Chebyshev's polynomial nth Chebyshev's polynomial for K. And so its K norm is mu n, and we consider nth root of this K norm denoted tau n. N nth root. And I claim that tau n, sequence tau n, converges. Well, it is a sequence of positive numbers and it is bounded. So first of all, note that tau n is bounded. Yes, well, if we denote by D not the transfinite diameter, but just naive diameter of our K, or this is just the biggest distance between 2 points. Then clearly tau n is bounded by d, because we can just take polynomial z minus z0, and where z0 some point. And clearly for this polynomial, it is already at most d to the n. Okay. So we obtain that. So we have a bounded sequence of positive numbers. So we only have to prove that lemma inf and lim sup are the same. So this is what we want to prove. And well, it is quite easy. There is always, well, here same nice trick. So the trick is the following: fix m, some m, and consider Tm of z. Oh, yeah. Oh. The polynomial Tm of z. And now for take arbitrary. So m is fixed for now. Take arbitrary n. Well, we do the Euclidean division. mq plus r. And we consider the polynomial p of z, which Tm raised to power q. And well, we obtain polynomial of degree mq. We need mq plus r. So we add something. We just add z minus z0 to r, where z0 is again some fixed point. It's monic of degree n. And so, what is its norm? Its norm is bounded. Here we have mu m to q. And here we have d to r. And it follows that our, or we can write it as tau m mq d to r. Okay, very well. Then this implies that our tau n to n is smaller than this norm, because it is the smallest norm. So we obtain the following inequality: tau m to mq d to r. And so tau n is bounded tau m mq over n d r over n. And well, mq over n is at most 1, so it is simply tau m drn. And when n tends to infinity, this will be 1, so we obtain that lim super tau n is bounded by tau m. And so far, n was varying, m was fixed, and for every fixed m, we showed that lim sup is bounded. And then, well, it's enough, because now we just take lim inf on the right, and we're done. So this proves the claim. So our sequence tau n converges. And its limit, it's called tau, or tau of k. And well, this is how it's defined, the Chebyshev's constant. Goluzin calls this Chebyshev's constant, and other authors. For k, but then one proves that what he defines as transfinite diameter, which defines slightly differently, is equal to this. So we just call it transfinite diameter. As I said once again, so Goluzin defines transfinite diameter differently, but then he proves that it is equal to this quantity. So we simply define transfinite diameter as this quantity. Now, okay, so this is the definition. Now let us speak on some simplest properties. First of all, for a finite set, it's obviously 0. Even for countable, I believe for countable, it is less obvious for me that for countable set, transfinite diameter is 0, but probably it is true. Well, it is less obvious to me. Probably it is true. Well, I don't know. Well, countable compact is finite, so yeah, then it doesn't make sense. Okay, so for finite set, k, tau of k is 0. Next, it is monotonic. If k prime is a subset of k, then clearly tau of k prime immediately follows from definition. And third property, that if we do affine transformation, then it behaves well. Lambda k plus nu is lambda tau of k. So if we do just translation, diameter doesn't change. If we apply some coefficient, then diameter multiplies by lambda. This is very easy. Simply the Chebyshev polynomial for the new one will be easily expressed in terms of the previous. So it is. Okay, so these are really easy properties that follow immediately from the definition. Now less obvious properties, but we will need them as well. Sorry. 4. Let P be a polynomial of degree m, monic polynomial of degree m. And we take the inverse image of our compact. Then the transfinite diameter behaves again nicely. It will be simply the transfinite diameter of K nth root. This is less obvious, and it will take us some time to prove it. Not that it is very hard, but, well, some work is needed. And property 5 is that the transfinite diameter of most important sets. First, of the closed unit disk should be closed because we need a compact. It is 1. And for interval -2, 2, it is also 1. And by using this affine transformation, this implies that the transfinite diameter of any disk I never know how to write disk with C or with K. Probably K, right? Depends on maybe of the country. Of any disk is equal to its radius. And the transfinite diameter of a straight line segment is 1/4 of its length. So here length is 4 and diameter is 1. Okay, so I will prove properties 4 and 5 now. So I will not go into proof 1 to 3 they immediately from definition. I will prove 4 and 5. And for 4, I need some preliminary discussion. Just the point is that, well, Galusin proves it, but he uses some algebraic trick, but since he was analyst and not algebraist, so he explains it not very bit weirdly. It looks a bit strange. So I would like to just speak on it. It's very, very simple, very easy, but I think it would be useful to say a few words. So we consider the following situation. So let X and Y be two copies of the affine line, complex affine line. So A1 of C, and also Y is also A1 of C. But I take two copies because I want to distinguish between points at X and points at Y. And here we choose a coordinate function . Here we choose coordinate z, and here we choose some coordinate that we call w. Yeah. Actually, well, it's not, well, what I'm going to say more or less extends to much more general situation. First of all, instead of affine line, we can consider projective lines or arbitrary algebraicers or whatever. But, well, I want to restrict to this case, which is exactly what we need. Now, we consider the polynomial in this z. We assume monic and of degree m. We will not always need that it is monic, but it will be convenient to assume. And we can see the map defined from x to y, defined by this polynomial, simply to every point with the coordinate z, we associate point whose w coordinate is p of z. So from z, we point with coordinate z, we associate point with coordinate p of z. Or, well, it's of course there is a dual construction. We have the field of rational functions on our x, which is of course generated by z, and the field of rational functions on our y, which is of course generated by w. And this simply defines an embedding c of y into c of x by simply w goes to p of z. The image of w will be this p of z. So we may consider this field as a subfield of this field. And we want to answer the following two questions. Which are not a bit vaguely stated, but, well, it will be more or less clear what the answer is. So first, assume that we have another polynomial in z. So which means some function on x. Some polynomial function on x. Can we associate to it in some natural way some polynomial in w? And second question with roles changed. We have q of w and associate some polynomial in z. Well, well, I don't specify what I mean associated natural way, but from the answer it will be clear what I mean. And well, to two, it's clear what it's obvious. There is only one way to associate it naturally. We just take the following. We simply we substitute instead of W P of Z, and we obtain a polynomial in Z, and well, there is the only natural way of associating. Or it can be viewed as the image of Q of Z under our embedding. Oh, sorry, self W. Oh, Q W, sorry. So this is really clear what we have to do. In one, it is somewhat less obvious, and we do the following. We write Q of Z as we factorize it, the product of so we here we want it to be monic. I want it to be monic. It will be enough for us. And then we associate to it a polynomial capital Q of W, which looks like defined a bit weirdly, but we will see that it is not weird at all. We just take the following. We take a polynomial whose roots are P of alpha 1, P of alpha n. But well, looks weird, but actually it is nothing but just the norm. So like here it is well, simply embedding from here to here. But from here to here, what we can do? Well, we can do many things, but in particular we can do the norm, and this is exactly the norm. So it is it's immediate verification that it is simply the norm. I let you do it. I don't want to do it myself. And if we want to calculate the value, if we take some gamma element in y in the W plane, how we calculate Q of gamma, capital Q of gamma? Well, we calculate it is small q of up to the sign beta 1, beta n, where beta 1, beta n is just the fiber above gamma. So sorry, m here, of course. roots of P of Z minus gamma, which is again clear. It's natural that it must be like this because, well, if it is norm, then its value must be the product of values on the fiber. So, and it's kind of immediate verification. Again, I skip the verification. It is you can try to do it yourself. So whatever. Okay, so after this bit, kind of almost tautological discussion, we can return to our statement. So return to statement 4. Let me remind what we wanted to prove. We have K is a compact. P of Z monic polynomial of degree M. And we want to show that the transfinite diameter of the P preimage of K is the transfinite diameter of K raised to power 1 over M, 1 over the degree of our polynomial. And we will use exactly the construction that I explained on the previous slide. So first, let Tn of Z, so just to simplify the notation, I denote this preimage as K star, and everything related to it will be star. So in particular, T star n of Z is Chebyshev's polynomial of level n for K star. Oh, sorry. For K star, and just normal Tn of W for K. Okay, so let us start from Tn of W, and we have some polynomial. We have Chebyshev polynomial on K, and we want to produce some polynomial on K star on the inverse image. And this is, as we have seen, this is easy. We just take Tn of P of Z and consider this is polynomial of degree Mn on with K star. You can see that on K star. And what is its norm on K star? Well, it's clear because we take, when we take P Z in K star, with P of Z will be on K, so its norm will be exactly the norm of Tn on K. And it is tau n raised to the power n. But what is this? This is bigger than tau mn star, this is for K star, raised to the power mn. Because it is not, well, we can only know, oh, sorry, this is greater or equal than, not well So on the other hand, Tn of P on K star, it must be greater or equal, it's of degree Mn, so mu Mn star, or this is tau Mn star raised to power Mn. And so what we obtain? We obtain that tau Mn star raised to power Mn is bounded than tau n raised to power n, and so this will be tau n 1 over m. And taking the limit, we obtain, because n is arbitrary, the tau star is bounded than tau 1 over m. So we proved inequality in one direction. We want to show that these two quantities are the same, but now we proved inequality in one direction. To prove in the other direction, we now start the Chebyshev on K star of degree n. And you remember we consider the polynomial like this. If alpha 1, alpha n are its roots, then we take P of W. We take P of W as, well, it's norm, so which is given by, sorry, P not good, P is already occupied. Let me call it, how we call it, Q of W. Oh, capital Q of W. As W minus P of alpha 1, W minus P of alpha n. And we have seen that if gamma is some point in K and beta 1, beta m roots of P of W minus gamma, then this beta 1, beta m, just by the definitions, belong to K star. And so, and Q of gamma is Tn star of beta 1 up to the sign, Tn star of beta m. And this implies that the norm of Q with respect to K is bounded, the norm of Tn star with respect to K star, we take product of m values, so we should raise to power m. But Q is also of degree n, so this means that the norm of Q with respect to K is at least tau n raised to n. And this is tau n star raised to mn. So we obtain that tau n raised to n is bounded by tau n star raised to mn, or tau n 1 over m is bounded by tau n star. Again, taking limit, we obtain that tau 1 over m is bounded by tau star, And so we had inequalities in both directions. We had in this direction and we have in this direction. So the two quantities coincide. So we have that tau equal to, sorry, tau star equal to tau 1 over n. Or this is exactly what we wanted to prove. So any questions on this? It looks a bit notational, I agree, but well, I don't know how to explain it better. So this is kind of, well, this is more or less analog, this of the height inequalities, that when how height behave under morphisms of degree d. So for those who know heights, it is it's more or less must look natural. Yeah. Now let us speak on property 5. So property 5 was about the transfinite diameter of disk and straight line segment. So we take as K now closed disk. And we want to calculate its transfinite diameter. Just take some polynomial. Some monic polynomial. Well, P of Z, Z n plus a n minus 1 z n minus 1 plus etc. plus a0. And now what we know about, well, pk, well, we know that biggest value it takes on the boundary by the maximum principle, which implies that pk is greater or equal than the integral, the average with respect to this boundary, so which is so looks like, oh. So as an accident like last time, looks like my computer, my tablet is a bit warmed, so I should restart the screen. I'm sorry, I stopped share and I should restart it. Now it works, so I can restart it. Okay. So the integral squared, and here of course is also squared, dt. So it's bounded from below by this integral. And this integral is, of course, by Parseval, we can easily calculate. It is just 1 plus a n minus 1 squared plus etc. plus a0 squared. And this is at least 1. So we obtain that whatever is the polynomial, its norm is at least 1 for any monic polynomial. On the other hand, if we take the polynomial Tn of z as z to the n, then its norm is exactly 1. So we obtain that mu n is just 1, and so tau n is also 1. So all of them are 1s, and we obtain that tau is 1. So the transfinite diameter of the disk is 1. This is very easy. So the k-norm of any polynomial is at least 1, and we have one polynomial whose norm is exactly 1. Okay, with interval, it's more or less the same, but slightly trickier. So if we take now k as interval minus 2, 2, and we take p of z, again, some polynomial of degree n. And, well, we may assume that the coefficients are real. Because k is real, and so if we have some imaginary coefficients, they only may increase the norm. So they cannot decrease the norm if we add some imaginary part. So we may assume that p of z has real coefficients. And then what is exactly, well, we just parameterize by cosine the points on our interval. It's maximum of p of 2 cosine t, where t runs 0 to pi. Now, if we write p cosine t, and we know that p is monic and its coefficients are real, then p of 2 cosine t will be some expression involving cosines of multiple angles, like nt, n minus 1t, and so on. And what is important, because since it is monic, here the nt, the coefficient, must be just 2. Or if we take 2 cosine nt, so there will be coefficient 1. So this is important. So here we have just 2 cosine nt, and plus other terms, a n minus 1 times 2 cosine n minus 1 t plus etc. plus a 0. But here it is no coefficient with 2 cosine nt. And we denote this guy as q of t. So this is some trigonometric polynomial Now, what we obtain that pk squared is maximum of q of t squared and this is greater or equal, of course, than the integral again over 2 pi from 0 to 2 pi q of t squared. Well, I may put absolute value, so it's not needed. Everything is real. dt. And now again, we use Parseval. Cosines are well orthogonal. So we can again use Parseval. One should only be careful here a bit. So I believe it will be something like this, like 2 plus 2an minus 1 squared plus etc. plus 2a1 squared, but a0 will be without 2. I believe it is something like this. Anyway, it is not really important. What is important is that we have 2 here, so it is at least 2. And what we obtain that the square norm of pk is at least 2, and so the norm itself is at least square root of 2. So mu n is at least square root of 2, and tau n is at least square root of 2, 1 over n. So this means that tau, when we take the limit, we obtain that tau is at least 1. Now, to show that it is exactly 1, we use, I want to use classical, one can want to use classical Chebyshev's polynomials. I prefer to use some renormalization of Chebyshev's polynomials, like Dixon polynomials. What is Dixon polynomial is the polynomial defined by dn of 2 cosine t is 2 cosine nt. It's known that it is such a polynomial, or equivalent definition dn of z plus z minus 1 is zn plus z2 minus n. And the norm of this Dixon polynomial Dixon polynomial is 2, because it is 2 cosine nt, so the biggest value is 2. But, so what is interesting, we do not show that this is the best approximation polynomial. To show it, because we showed only that lower bound for the norm is not 2, we obtain lower bound square root of 2, and here we have 2. So, but to calculate the transfinite diameter, it is sufficient, because then tau n is bounded by 2, 1 over n, and so tau is at most 1. And so we found that tau is 1. So this is basically the whole theory about transfinite diameter that well, I wanted to tell, so not much theory. For I'm sure that for big part of the audience it's all well known and perhaps in a better form than I gave it, but well, I had to say something. And now I will state a crucial theorem that was used by well, actually main fact used in Dimitrov's proof. It's a theorem of Dubinin. Theorem of Dubinin, it tells about transfinite diameters of special kind of compacts called hedgehogs. They also can be called stars, or there are some other name, but I adore the name hedgehog, so I will use it. So hedgehog, so A0 will be kind of center, and then A1, AN vertices is the following guy. We take some point on the complex plane, A0, and then we just put straight segments to the other. For instance, here N is equal to 4. So this is A0, so A1, A2, A3, A4. Okay, so this kind of set will be called hedgehog. And of course, among the hedgehogs, there are some nicest. The regular and hedgehog is simply what? It is H of with center will be just at 0, and then the points will be n roots of unity: 1, zeta n squared, etc., zeta n minus 1. So like here, I'm not very good in drawing pictures. Sorry. So assume that this is a unit circle. So circle is not a part of hedgehog, only the segments. So this is the case n equal to 8, I believe. And well, I will simply denote it Hn. And the transfinite diameter of Hn is very easy to calculate. If we take a polynomial p of z equal to z to the n, then what is Hn? Hn is simply inverse image under this polynomial of the unit interval of 0, 1. And this implies that the transfinite diameter of Hn is transfinite diameter of this 0, 1 raised to power 1 over n. But this is, we just saw that transfinite diameter of a segment is 1/4 of its length. So it will be 4 to minus 1 over n. Okay, and this is for this regular hedgehog. Now what happens with the arbitrary hedgehog? Theorem of Dubinin proved also long ago. This is the newest result used by Dimitrov. All the other results used in his proof are much older. And I think it is theorem that you could also explain to faculty in 20s, he would probably understand it. It's the following. If instead of roots of unity, we take some arbitrary points on the unit circle, we also obtain some hedgehogs. So let A1, AN be some points on the unit circle on S1, which means it's simply A1 complex numbers of absolute value 1. And we consider this kind of hedgehog. For instance, here n equal to 5. And Dubin's theorem tells that its transfinite diameter is always less or equal than the transfinite diameter of the regular. So the regular among all these n hedgehogs with the vertices on the unit circle, the regular has the biggest transfinite diameter. This is the theorem of Dubinin. And an immediate consequence, if we no longer assume these guys lying on the circle, just arbitrary complex numbers, then the transfinite diameter of this general hedgehog is bounded by this factor, which is crucial, 4 to minus 1 over n, and simply the maximum of the absolute values. And this is where the house of algebraic number comes out from this maximum. Well, so corollary is indeed, it follows because we simply, by the property that a part of a hedgehog has smaller transfinite diameter, a part of a compact has smaller than the bigger one, the monotonicity, and affine transformation. So it is immediate from the easy properties of transfinite diameter. Well, concerning the proof, so I was hesitating and I decided that I will not, most probably, I will not prove the theorem of Dubinin in this course. So, well, I'm afraid that for this I will need a bit more complex analysis. I think probably I will need one more lecture to give a full complete proof of the theorem of Dubinin. And well, if I really have a lot of time left, I will probably reconsider this and maybe give some idea. But for time being, we just take this for granted. And this will be the only deep result that we take for granted, the theorem of Dubinin. All the other things I'm more or less proving. So this is the only thing that I'm not going to prove. Okay. So this is all what I wanted to say on transfinite diameter and hedgehogs and theorem of Dubinin. I still have like quarter an hour left. First of all, are there any questions before I start the new part of the course?
Is there a reference of this paper?
Yes, Purushottam.
Yes, the reference of the paper. Of the
Someone wants to ask a question?
can you hear me? Can you hear me?
Who?
Purushottam here.
Purushottam. Well, I hear you, but do you have a question or you just?
No. I wanted to ask: is there a reference of this paper of Dubinin?
Sorry.
The result of Dubinin. Do we have a reference?
Yeah, I can upload. I have the article. I have the English translation.
Okay,
the problem
perfect.
is that English translation is really disastrous.
Nice.
Very bad. There is also a book of Dubinin,
okay.
and it proves there in some chapter. And there is some nice write-up due to Harry Schmidt. Harry, are you here? No, Harry today is not here. There is some nice write-up, but one should figure out why what Harry wrote actually proves the theorem of Dubinin. So one needs some bridge.
Okay.
Yes. So I will. So I will upload the article of Dubinin, but please, so be careful. It's really the translation is
okay, no problem. Sure.
Extremely bad, yes.
Okay.
And I will also check a chapter in his book, and there are some materials. I will upload something. At this moment, I did not upload. Okay, good. So then we can start the section 3 or chapter 3. And this is theorem of Poya. It's also related to transfinite diameter. It's an old, beautiful classical theorem. It is the following theorem. So let K be a compact as before. And we assume now that K is symmetric with respect to x-axis. Means that symmetric means that if Z is in K, then also the conjugate is in K. Next, we take the complement in the extended, in the Riemann sphere. So, and I will assume again that this is simply connected. This assumption is actually not needed. The symmetricity is needed, is absolutely nothing but all without. Here, one does not really need, but it will simplify, slightly simplify the argument, so it doesn't really matter and sufficient for us, because we will apply when K is a hedgehog, and it's clear the truth of hedgehog. And we take a function which is holomorphic or regular on this complement. And well, it was also regular at infinity, so it has Taylor expansion at infinity. It is, so it starts from constant term, A0, and then coming the negative powers of Z, because it's expansion at infinity. A1Z plus A2 over Z squared plus etc. Well, in article of Poya, he considered near zero, not near infinity, but for our applications, it would be more convenient to work with expansion at infinity. So. And what is the theorem of Poya? It was proved actually in the same year when Fekete introduced transfinite diameter, and Poya does not use the terminology transfinite diameter in his article. He speaks in terms of what is called conformal radius. I don't want to go into these details. Perhaps I will say, if I decide finally to prove the theorem of Dubinin, perhaps I would mention what is the connection. But anyway, and it was not the first work on this kind. There was some previous work by Borel, Fatou, by Seton Carlson, and so on. Anyway, Poya established really a very, very general result. So in 23, so you see 100 years ago. Assume that two things. That first, the transfinite diameter is strictly smaller than 1. And second, that the coefficients are integral. And then it is only possible when f is a rational function. So we cannot have transcendental function. We cannot have transcendental function or even algebraic function with which expands to with integral coefficients and at infinity, and which is regular on a complement of a small set of small transfinite diameter. So it's certainly very, very best possible because well, you can give already which example. Well, I think there are many examples where just with k the unit disk. Well, it's many functions which have the unit circle as a natural border of natural boundary of analyticity. So it's really best possible. You cannot even write here less or equal. So it must be strictly smaller. And well, I will prove this theorem on the next lecture. And well, how it will go. So the proof requires another very classical theorem. also Hungarian theorem. Theorem of Fekete-Szegő. This is 55. So it will be not the proof that Poya gave himself. Poya used what is called the Chronicle Criterion. What is Chronicle Criterion? It's the following. We can see the determinants. Well, A0, A0, A1, A1, A2, A0, A1, A2, A1, A2, A3, A2, A3, A4, etc. Well, the law is clear. And the function f is rational if and only if, starting from some point on, this discriminant vanish. These discriminants from some point on. I will give a proof based. I will give a proof based on this Kronecker-Szegő theorem. I don't have time now to state it. I will do it on Monday, and it is a proof due to Raphael Robinson. It does not use this Kronecker criterion. I did not upload the article of Robinson because it was easier for me just to listen what Vesely and Dimitrov explained than to read the article of Robinson, but I can also upload it. I think something like 69. Okay, so I think it is enough for today. So if there are any questions, I'm ready to listen.
Yuri, hi Yuri, can you hear me?
Yes.
So the criteria, just rational, the determinants vanish. There you don't need any. I mean, it's true for any field, right? This criteria, right?
Yeah, well, yes, but point is that when you deal with integers,
you need to.
It's easy to show that they vanish. You should just show.
Okay, yeah, checking would be easier. I see.
Well, easier. I don't say easier. I say easier.
And the rational function also, you can make sure. I mean, define as a rational function. You can make sure the both sides are monic or something. The numerator and denominator or something.
Sorry.
You have a power series over Z. You are showing it's rational. So I am assuming it will be defined over Z or both the numerator and the denominator. Fx by qx, where f and
I don't understand
the theorem. Polya, yeah, f is a rational function. Originally,
but if the coefficients are rational, then they must be defined over Z. Yes.
But can you make sure that something is monic or something? No.
I don't think. Well, it's rational function. I don't think it's monic. Yeah. No, I don't think so. Basically, you take any rational function and statement to
Will be true, yeah, over Z. Yeah.
irregular, yes. So,
Okay, so anybody else has any question? No.
okay, so as I did last time, I will transform this into PDF and I will upload it into the folder. And we meet next time for the proof of the theorem of Puya and theorem of Fekete-Segel.
Yes, on 29th.
And then we will see what we do further. Okay.
Yes, the next lecture is on 29th, right?
Yes. So this will be probably the hardest lecture because I will prove two hard theorems.
I see.
Yeah. Okay. So.
Okay. Thank you, Yuri.
Okay. Bye. Thank you.